In this video, we're going to look at electrical power and also AC and DC current for GCSE Science. So the fundamental thing for this part of the unit, and the thing that comes up the most in exam questions, is the use of this formula. Now, students immediately get confused because they will be familiar from the forces or the mechanics unit in Key Stage 3 that power is the rate of transfer of energy. And now we're telling them that power is current times potential difference. So they do get confused, and you've got to really make it clear that they were talking about electrical power. And when we're talking about electrical power, we need to use the electrical quantities, current and potential difference. If we're talking about mechanical power, we use this. And then they'll get confused when actually there's an electrical question that says something like an electrical device transfers 100 joules in 10 seconds. What's the power? And they'll say, well, you've just told me we need to use current and potential difference. So at that point, you probably need to break it down really simply and say we just need to look at what values we've been given. If we've been given joules and seconds, we use this formula. And if we've been given amps and volts, then we use this formula here. This formula is not immediately obvious why this is true. So let's explain that. Now, this explanation is not crucial for GCSE exam paper, but for the more able students, it's kind of very useful for their conceptual understanding. So current is the rate of flow of charge, and potential difference is the energy or the work transferred per charge. So simply stating this in words with the proper formal definitions actually helps us explain exactly why this is true. Because what is power? It's the rate of transfer of energy. So now we've got the rate of flow of charge and the energy per charge. So we've got the rate of flow of charge, all right, because the charge and the per charges cancel. If that's not immediately obvious, let's write it out in simple form. Current is the rate of flow of charge, and potential difference is the work done per unit charge. Two formulas that students do need to know at GCSE. So what happens? The charges cancel, and we've got power is work done per time, which is exactly what we said here, energy per time. Right? Obviously, energy and work done mean the same thing. Now, this is not the only form of the equation that students need to use, because we have this other relationship here. What happens if we substitute this relationship into this equation? So there's two ways we can do this. We can substitute V in, and we can get power is I times R, or I squared R. Or we could equally say that I is V over R and substitute this into power is current times potential difference, and we could get power is V squared over R. Now, this is not GCSE, or not AQA GCSE. This one is AQA GCSE. So this is the one we need to spend our time and efforts on. But if you've got a more able class, it's worth at least showing them or challenging them to do this, just for their understanding and mathematical fluency. Now, this equation here does cause students difficulty because they have this squared here. So if they've been brought up on formula triangles, they really struggle now because this is really hard to use in a formula triangle. And is another reason why formula triangles are not a good solution. So my tip for you for doing this is to really break it down. If you've got an able class that is capable of rearranging, you can teach it properly. You can say, actually, we should rearrange it like this. We can rearrange it like this, etc. If it's a less able class, I would get them to very simply list the quantities. So from the question, they could say something like power is 100 watts, resistance is, I don't know, let's go 5 ohms, and then write it out like this: 100 equals I squared, or sometimes even a question mark squared if it's a really low ability set. A question mark for some reason seems to work better, but we should use simple if possible, times by 5. Then you can say divide by 5, divide by 5. So 100 over 5 is I squared. So 20 is I squared. And then the square root of 20 equals I. And then they can plug that in their calculator and get the answer. And actually putting in the numbers like this is a lot more simple for students, especially when you've got this kind of more complicated way of rearranging it. Why have I included AC and DC electricity in this? Well, it's mainly because when we talk about AC and DC, we're talking about how we deliver electricity. So if we look at DC, then we have a constant potential difference. So a battery will provide a constant potential difference, it doesn't change, and obviously a constant power output. You can also get DC generators that do this. AC, on the other hand, is constantly varying. So the current and the potential difference is constantly varying. The frequency, so how many times it changes every second, for the UK is 50 hertz. And the potential difference, or the voltage, is 230 volts, things that students do need to remember. Now, interestingly, and this is beyond GCSE, this value here is not 230 volts, the peak one. The 230 volts is the average potential difference and is actually about here. Right? It's actually related to the square root of 2. And I'm not going to go into this, it's very much A-level physics, but I highly recommend looking this up in more detail because it is really interesting, and it obviously relies on the mathematics of averaging this sine wave here, because this is a sine wave. And students generally do know what a sine wave is from their maths lessons. Now, a really nice thing to get students to think about is, if we've got potential difference and it's going positive, negative, is not the average actually zero? Are we not saying that the average voltage is zero? And therefore, if the average voltage is zero, how can any energy ever be transferred? Well, now it's useful to link it back to power. Right? What is power? Power is current times potential difference. So potential difference is doing this, current is doing this. What is the power transfer? It's current times potential difference. So therefore, the power transfer is always going to be positive, because two negatives times together will always be positive. So the negative current and negative potential difference will give us positive. So we are actually transferring energy, because the power is always positive. And that's why I've linked it in to this topic. There's a really great website, which I'll link to in the description, called GridWatch. You can just type in GridWatch into Google and you'll get it. And it tells you the state of UK mains at any instant. It will tell you the exact frequency. And it will also tell you the breakdown of energy sources, so how much is fossil fuels, renewable, etc. It's quite an interesting website to actually link this to real life and show students that this does very obviously relate to real life.